Have you ever come across a puzzle that's like over 150 years old, but is still being used to push the boundaries of modern AI? Well, let's dive into one. We're talking about the legendary 8 Queens puzzle. On the surface, it seems pretty simple, but underneath, it hides this incredible complexity that has fascinated mathematicians and programmers for generations. Okay, so first, let's talk about the star of our show, the queen. In chess, she is an absolute powerhouse, right? From just one square, she can zip any number of spaces up, down, sideways, and diagonally. And it's this huge range of motion, this power, that makes this whole puzzle so darn tricky. So here it is, the big question. How in the world do you put 8 of these super powerful pieces on a standard 8x8 chessboard so that not a single one can attack any of the others? You know, that means no 2 queens can be in the same row, same column, or on the same diagonal. Just take a second, try to picture it. It's way harder than it sounds, isn't it? And that simple-sounding question, well, it brings us to the absolutely massive scale of this problem. Because stating it is easy, but actually finding a solution, let alone all 92 of them, is a whole different ballgame without a really smart strategy. Now, the most obvious way you might try to solve this is what programmers call the brute force method. This means you would literally try out every single possible combination of putting 8 queens on the 64 squares. Imagine trying to find one specific grain of sand on a beach by picking up and checking every single one. Yeah, it's thorough, but wow, is it inefficient. So how many combinations are we talking about? Get this, it's just over 4.4 billion. Let that number sink in for a moment. Even if you had a computer checking thousands of these layouts every second, it could still take a whole day to get through them all. And this is a perfect example of why brute force is almost never the right answer in computer science. And here's the real kicker. The problem gets exponentially worse the bigger the board gets. This is what we call an intractable problem. As this quote shows, if you scale this up to a 1,000 by 1,000 board with 1,000 queens, a normal algorithm would take thousands of years to solve it. So yeah, we clearly need a smarter way to do this. Okay, so if brute force is out, let's move on to our first clever solution. This is the classic computer science approach, the way early programmers figured this out, not with raw power, but with pure systematic logic. The technique is called backtracking, and honestly, the best way to get it is to think about solving a maze. You go down one path, right? And if you hit a wall, a dead end, you don't just stand there. You turn around, you retrace your steps to the last choice you made, and you try a different path. Backtracking does exactly that, but with placing queens. So here's the basic idea in action. The algorithm places a queen in the first row. Then it tries to place another queen in the safe spot on the second row, and so on. But, and this is the key, if it gets to a row where there are no safe spots left, it backtracks. It goes back to the row before it, moves that queen to the next possible spot, and starts moving forward again. It's so smart because it completely avoids wasting time on entire branches of possibilities that it knows are doomed to fail. So we really have 2 totally different ways of thinking here. On one hand, you have backtracking. That's our meticulous detective. It systematically checks every clue, every path, until it's guaranteed to find all 92 solutions. But then there's this other, more modern way, which is less like a detective and more like a creative evolver. So, if backtracking is the logical detective, let's meet the wild artist. This is the AI approach, and it uses a really cool technique that's literally inspired by biology, the genetic algorithm. A genetic algorithm works just like evolution and natural selection. Seriously, imagine you're breeding racehorses. You'd take your fastest male and your fastest female, breed them, and hope their kid is even faster, right? Well, this algorithm does the same thing, but with chessboard layouts. It starts with a bunch of random, terrible solutions, finds the fittest ones, the ones with the fewest attacking queens, and breeds them together to create a new generation of slightly better solutions. And this is where it all begins. In Generation 1, the algorithm just throws queens on the board randomly. The result? It's a total mess, a disaster. We've got 6 queens attacking each other here. In evolutionary terms, the solution is not very fit. But hey, you gotta start somewhere. But then, after running the algorithm for a bunch of generations, letting the best solutions breed, mixing in a little random mutation, we get something much, much better. Look at this. The number of attacks is down to just 3. Our little population of solutions is evolving. It's adapting. And finally, after maybe thousands of these little evolutionary steps, bam! A fittest individual emerges. A perfect solution with 0 attacks. Now, it's not a guarantee it'll find a solution every single time, but it's an unbelievably powerful way to find really good answers to super complex problems without having to check everything. So you might be thinking, okay, that's a cool old chess puzzle, but why do we still care? We care because the methods we use to solve it are incredibly important. The n-queens problem is what we call a toy problem. It helps us build and test the algorithms that we then use to solve massive, real-world challenges. And if you need any proof of why these smart algorithms are so critical, just look at this table. Look at how fast the number of solutions just explodes. For our little 8x8 board, there are 92 solutions. Okay, manageable. But by the time you get to a 24x24 board, there are over 227 trillion solutions. It's just mind-boggling. This kind of insane growth is exactly why we need these brilliant algorithms to cut through all that noise. And this quote from Professor Ian Gent really just hits the nail on the head. The techniques we're talking about, they aren't just for games. These exact same problem-solving approaches can be adapted for all sorts of things, like cracking codes, optimizing flight paths for an airline, or even mapping out complex financial markets. So the 8 queens puzzle is so much more than a brain teaser. It's a training ground, a gym where we build the mental muscles and the programming tools that will solve the huge challenges of tomorrow. Which really makes you wonder, what seemingly impossible puzzles in medicine or logistics or even climate science are just waiting out there for the next evolution of these incredible algorithms?